All right, so your bell ringer for the day, you got 4 problems here. I'll probably just bounce down to the bottom where the one there, you can't see it that great, so we'll leave it there and see if you can figure it out. So the bottom one has the continuously compounded interest formula that I gave you guys yesterday, and we will definitely be using that here and a little bit in the future. Okay, so please pause the video and let people have a chance to work through these. Give them about 5 to 7 minutes. All right, back up to the top. So we want to write an equivalent exponential function for natural log of 14.2 equals x. So you got to remember what the base of natural log is. If you need to, you can rewrite it as log base e of 14.2 equals x. And that way you can kind of know what you're dabbing here. So we want to dab from one side to the other. Boom, boom. We get e to the x equals 14.2. And that is it. That's all you had to do is just rewrite it. Okay, that's a one-step problem. Second one, solve the equation. So remember when we did these yesterday, we needed to isolate that exponential. That guy right there, we got to get by itself. So first we got to move the 6. And then you get 4e to the negative x equals 6. Next step, divide the 4. Okay, those will cancel. We get e to the negative x equals 6 over 4. Reduce the fraction, so you can take a 2 out of the top and the bottom, which would give me a 3/2. Okay, next thing that we could do here, you can switch this from an exponential to a logarithm, and that would help you out. But the stuff that we did yesterday, which I said I prefer more often, which we're going to be doing today, is you want to natural log both sides. Okay? Because when you natural log an e, when you natural log Euler's number, that cancels it out. That goes away. And we're left with just that exponent, so negative x equals natural log of 3/2. Which then you're just going to put that in your calculator, multiply it by a -1, and that's your answer. Okay, so that'll give us about a -0.4055. So 10 thousandths, that's 4 places. And you probably got 0.4055, but remember we have this negative over here by the x, so we need to multiply that through, and that gives me the negative 0.04 or 0.4055. Excuse me. All right, solving the natural log equation here. So for c, you can do it just like we did with a. You can dab both sides, or dab it, and change it to exponential. I'm going to use that exponentiation method that I talked about yesterday. That was a big word that I said towards the end of class. You exponentiate something. So what is the base of a natural log? Well, up above we said it was e. So I'm going to raise both sides. Just going to kind of do it here. Both sides of the power of e. Okay? That'll cancel out my natural log. Then I'm left with 2x plus 3 is greater than e to the -3rd. E to the -3rd power, you can do that in your calculator. So let's move stuff around, get the x by itself, and then we'll just throw it in our calculator to see what we get. So -3, that turns into 2x. And remember that e, you can't really add or subtract that -3 from it, so we just have to write it like this. Because e is kind of like pi. You just want to leave it as an e or a variable. And then we need to divide both sides by 2. Okay, so this is what you're going to be putting in your calculator right here. That's going to give us a decimal. So if I put that in my calculator, I get, so e to the -3rd power minus 3 divided by 2. That gives me a -1 point. So x is greater than -1.4751. Okay, and then this one has one more step to it. I showed you guys in the homework video. We need to make sure the stuff on the inside of this natural log is greater than 0. So you make a little inequality like this, 2x plus 3 is greater than 0, and then you solve for x. So we get x is greater than a -3/2. So we got to have this inequality and this inequality here in order to write our answer. So the smaller number will go on the left, the bigger number will go on the right. Negative 3/2, that's negative 1.5. So actually, we just need the bigger number because we're greater than on both of them. So whichever one tells us the bigger number, that's the smallest that we can put in there. So this one right here, that one's just going to be our solution because that would overtake the other one. So x must be greater than a negative 3/2 or 1.5, whichever way you wrote it. Okay, that one would be the solution. All right, if you don't understand that last part, it's not extremely important as long as you understand how we can get to this answer. Okay, like I said on the video before, I'm not going to give you any of these on the test. I just wanted you to see them. They do take a little bit more brain power. Okay, but I just wanted you to see them and try to persevere through them. So, last problem here is continuously compounded interest. So remember when we see continuous, that means that's Euler's number coming into play. That's the PERT formula. Okay, PERT is the continuous compounded interest formula. So we just plug stuff in. A is what we're looking to find. So you put money in there, you look and see how much you get out. A is what we're going to get out. So we're going to have A equals, P is my principal, so we're putting $2,000 in there. And our account pays us 4% annual interest. So remember the E, so that's principal there. The E is just Euler's number. My rate is 4%, so that is 0.04. And we're doing that for, we're saying how long will it take for the money to double? So we're not doing it for a certain amount of time. So that T should be just up there. So how much money is double 2,000? Well, we do have an amount. We're just going to figure out how long it takes to stay in that account. So 4,000 would go here. And then we need to solve for T. Okay? So to solve for T, we're going to have to divide both sides by 2,000. Okay? And that'll give us a 2 on the left. And then we'll have e to the 0.04 times t. How do we get rid of the e? We want that exponent down. So we need to natural log both sides. Natural log, natural log. That'll get rid of my e and leave me with 0.04 times t over here. Natural log of 2. So then the last thing you got to do is move the 0.04. So divide by 0.04. Divide by 0.04. So natural log 2 divided by natural log 2 divided by 0.04. It is about 17.33. So t equals 17.33 years. That's quite a while, but we're looking to double our money, so that makes sense. Okay, so there is your bell ringer. Now you guys can compare homework for 5 to 10 minutes. I did make a video that I uploaded in Google Classroom if you wanted to look at that right now for those 5 or 10 minutes. And then after those 5 or 10 minutes are up, we will begin with the lesson. So the sub, can you please pause the video and give people a chance to look over homework and make sure everyone turns it in when the 5 to 10 minutes are up. All right, so we're going to go through 610, and that is using logarithm to solve exponential problems. So this is the one I said there's a lot of word problems here. You should have a note sheet in front of you. It should say 6-10 Study Guide and Intervention on top. I'm going to be pretty much going through those problems to help you out. So that'll be our notes for the day, so it's like a note sheet. And I'm going to take care of one problem on your homework to kind of give you a jump start. Okay, so we're going to be learning how to use logs to solve real-world problems. Okay, so the two equations on the top of your worksheet there, there's exponential growth and exponential decay, and we had something really similar to that yesterday. Remember when we had e to the x and e to the negative x? This is very similar, but these are more written as formulas. Okay, so I would circle these on your notes or make sure you see where they're at. We have AE to the KT, where A is the initial amount of something, then k is going to be like our growth factor or rate of growth, okay? So that's kind of like the rate. And sometimes that could be a nice decimal, sometimes that could be a decimal that has like 4 or 5 places to it, okay? It depends on how it comes out of the problem. T is time, and E is just that button in your calculator, that e to the x button, okay? So wherever the natural log button is, you can find that e to the x button. Okay, so those are all the pieces for these equations, and then, so this is continuous growth up here because the exponent is positive, and down at the bottom here, that's continuous decay because of this negative exponent. All right, so if you see negative exponents, that means decay, or if you see something in a word problem that says it's decreasing or getting smaller, or half-life or something like that, you're going to use the bottom one. So, let's get started. So the first problem, population in 2000, the world population was estimated to be 6.124 billion people. In 2005, it was 6.515 billion people. Determine the value of k. All right, so we're going to find a rate here. Determine the value of k, the world's relative rate of growth. Okay, the value of k, the world's relative rate of growth. Which that's kind of a redundant sentence there. Okay, so I must have accidentally had a typo. But we want to find the value of k here. So it's a growth equation, so that means we're going to use f of x or y equals a e to the k t power. That's the one we're going to be using. And I know it says f of x on the top. I'm just going to change it to a y. Okay? And I didn't explain what this was. That's usually like what you get out of the equation, or maybe this is like an end result. Okay? So maybe the population grew, that's what it grew to. So we do have that information in our equation. We have our starting population there, and we have our ending population there. We have a couple time pieces in there. So 6.515, that's the end result. So here we go, let's change it, let's plug it into our formula here. So 6.515, that's the ending population that we had. We started with 6.124. Again, these are in billions of people. So we have continuous growth, so that's the E. K, we don't know, that's what we're trying to find. And then time, we're going from 2000 to 2005, so it's K times T. Now, to make it look a little bit better, do we ever write K5 in the top? Probably not. Let's rewrite it as 5K. That way we always put that number in front of the variable. So we have 5K in the exponent up there. We did some problems with E yesterday. Let's get the E by itself, natural log both sides, bring the exponent down, and we can solve from there, okay? So the first step is divide by that 6.124 on both sides. That'll get rid of it over here. So we have, let me move this stuff up here. Oops. Let's just bounce this up here. So we have now just the E over here. So we got E to the 5K equals 6.515 over 6.124. How do we get rid of the E? We want to natural log both sides, right? Because remember, this right here, those are inverses. Natural log is the inverse of E. So we want to do the inverse to cancel out the E, but we have to do it to both sides. So those cancel here. Then we have just a 5K on the left. 5K equals natural log of 6.515 over 6.124. Those are inside the natural log there. So then we just have to divide by 5, and then you get your answer. So we take this, divide by 5, throw it in your calculator. So you really have to be careful when you're putting these numbers in your calculator. Make sure you have all the decimals, make sure you have them in the right spot. So natural log, that's the LN button, 6.515 divided by 6.124. Okay, that's the stuff inside the natural log. Make sure you close off your parentheses, as we have here. So you'll do that, and then divide that by 5. And we get K, our continuous rate of growth, is going to be 0.01, and it doesn't tell us what to round to, so let's go to 4 decimal places. 0.124. That's our growth factor, the relative rate of growth. So we had to use natural log to get rid of that e in there. We got to get the e by itself, natural log both sides, divide by 5, and then you get your K value. Okay? So then you can use that in the next problem. So when will the world's population reach 7.5 billion people? So now let's use K to figure out when or how long it'll take us to get to 7.5 billion people. So we need to use that beginning amount, and this is going to be our ending amount now, 7.5. So we'll put 7.5 billion here. And then what did we start with? 6.124 billion people. That's what we started with in 2000, according to our problem. We have E, because it's continuous growth. Now we use that value of K up there, 0.0124 times T. And now we're doing the same exact thing that we just did to find the K value. Now we have to divide the 6.124, take the natural log of both sides, divide by that 0.0124, and then you will have T. So let's do that. So let's divide by 6.124 on both sides. Right there and right there. So now we have 7.5 over 6.124 equals e to the 0.0124 t. Natural log both sides. So that cancels out over here. All right, so you can see that it cancels out. I'm just going to erase it. All right, so you saw that canceled. Boom, it's gone. Now we just have this stuff over on the right-hand side here. So how do we get rid of the 0.0124? You're going to divide it. So divided by 0.0124. Divided by 0.0124. Boom, boom, and then whatever we get from there, we plug it in our calculator, and that will tell us how long it takes us to get to 7.5 billion people. So you take natural log of 7.5 divided by 6.124, close off your parentheses, divide that by 0.0124. And it takes us approximately, and you can round to the 4th place here if you want to. I'm just going to round to the 100th place, so that's the 2nd spot. 6.35 years. So it would take us about little over 16.25 years to get to 7.5 billion people. So that's how those problems work. So remember yesterday I said you're going to be using the natural log of both sides stuff a lot. That's really powerful when you get to these real world models and stuff like that. Okay? So next problem, so that's at the bottom of your worksheet. And I'll probably just do, I'll do all of these in the video, and you guys can skip forward if you want to. But I'll probably do this one, and then the next one, and then I'll do your homework problem, just for the sake of the length of the video. All right, so carbon dating, this is used in carbon dating a lot, but as you see, the formula that they give you there, that's already that A, E to the KT stuff. The rate of growth there, this is a decay model, okay, because carbon dating, if you guys know, they use that for like dinosaurs and stuff like that, fossils. So that is an amount of carbon that's decayed over time. So it's a negative exponent, and it's kind of a long exponent, so you have to be careful when you're using your calculator. Okay, so use the formula given there, where A is the initial amount of carbon-14. Okay, you don't really care about the 14 in there, so don't get hung up on that. That's just talking about the compound that we're looking at. T is the number of years ago the animal lived, and Y is the remaining amount after T years. Okay, how old is the fossil that's lost 95% of its carbon-14? So you got to remember, A is the initial amount. And these are one of those problems that it doesn't tell you what the initial amount is. It just says, how old is it if it lost 95% of its carbon-14? Well, remember that medication problem we had in the homework? If you're not told how much you start with, then you assume that you start with 100%, right? So that would be my A. My A is 1, or 100%, okay? The Y is what we're left with, or what we're trying to use. So we started with 100%, we're left with 5%, because it says we lost 95%. So that means my Y is just going to be 0.05, because we lost 95% of our carbon-14. Okay, so if you lose 95%, that's 1 minus 0.95, you get 0.05. So then we can take that information and plug it into our equation and find T, because we're looking for age here. We're looking at how old something is. So we have 0.05, that's our ending amount, right, because we lost 95%. Our starting amount is 1, or 100, e to the k, which is that negative 0.00012 t. And remember, if you got 1 times something, don't overcomplicate it. You don't really need the 1 there. 1 times something is itself, so let's get rid of that. So we have that. Should be a pretty straightforward step from here. How do we get rid of the e? We want that exponent down. Natural log it. Natural log both sides, right there. Those will cancel. And then we'll have natural log of 0.05 equals negative 0.00012 t. How do you solve for t? Divide by that long decimal on both sides. Put that in your calculator. So those will cancel out. We put this stuff in our calculator, and we're going to get t equals something. So if we do that, natural log of 0.5 divided, or 0.05, sorry. Careful with those decimals. Natural log of 0.05 divided by negative 0.00012. And we get 24,964. And we'll round that. 24,964. We'll go to the 100th spot again. So 44 years. That's old. So 24,964.44 years. That's where they get the big numbers from in carbon dating. So when they say something is millions and millions of years old, they look at how many atoms of carbon is in a fossil or something like that. They use this formula or something similar to this, depending on the creature, and then they can figure out how old it is. Okay, so let's try the second one. I want you guys to see if you can figure out the second one on your own. So please pause the video, give them a few minutes, see if they can figure it out, then you can start it back up. All right, so back to this one. Now we have to figure out how old a skeleton is that has 95% of its carbon-14. So again, we're starting with all of it, which would be 100%. We have 95% of that left. So that means my y will be 0.95 because we have 95% left. So let's set it up. 0.95 equals 1e to the negative 0.00012 t. We're going to figure out how old this skeleton is. Okay, we don't know if it's a person or an animal, so we're just going to go with a skeleton. Remember, the 1 doesn't matter. So really, your next step is to natural log both sides. So I'm going to just kind of write that there. The 1 doesn't matter, remember. So the natural log and e are going to cancel out. Then we have natural log 0.95 equals negative 0.00012 t. Divide by that on both sides. And then let's put it in our calculator to see how old this thing is. So natural log of 0.95 divided by negative 0.00012. 427 years old. Say 0.44. Round to the second place there. Okay, so that's pretty old. So if you lose, apparently it takes a long time to lose a certain amount of carbon-14 because you think 95%, that's still quite a bit of it left. But it's like, think of things deteriorating. It takes a while for things to actually deteriorate and start to turn into dust, right? So we got 427.44 years. All right, so hopefully that makes sense. Again, you guys, we're using the natural log stuff here. We're taking natural log on both sides to cancel out e. That's the way we're going to be doing it on the tests and quiz, or the tests for next Tuesday. You're going to have some word problems like this, okay? So the next thing we're going to be looking at is logistic growth. And if you're looking at your worksheet there, logistic growth is at the bottom there. So that's a pretty fancy way to say that it's a population model that's going to level out at some point in time, okay? So that means that saturation here, saturation begins, the growth slows down. So I'm going to kind of give you a quick rundown of this one, and I'm going to work through the second one. If you need to look through, or if you want to know how to do this one, I'll have it at the end of the video for you to look at again. But I'm going to do one problem like this. The math is kind of heavy because the formula is not the best. But this example here is kind of applicable to me because it deals with fish. I like to go fishing. I know that if I catch a bunch of little fish, either I'm not doing a very good job fishing or there are too many fish in the lake. So that's that saturation. So if there's too many fish in a lake, then they start to slow down. They stunt their growth. All right, same thing begins with like deers in Nebraska. We need to have a population control, right? That's why people can hunt. Because we need to keep the population under control. Otherwise, you begin to have too many deers and they just saturate the population. So this first one here, what you're going to want to do is make a graph. So we have a fish in the lake here. You're making a graph. Okay, I'm just going to kind of set it up and I'll come back to it later. What I would do is we have to make an XY chart. So right down there, the little T, we're going to plug into that T. And we're just going to kind of see what we get, okay? So for your XY chart, I would probably go by tens maybe, so 0 years, 10 years, 20 years, 30 years, 40 years, and then maybe you could do 100 to see where it starts to approach, and maybe you can do 200 if you wanted to, but I'll come back to that. I want you to understand that these things have asymptotes, right? Because they are exponential functions. Exponential functions have asymptotes. They're horizontal asymptotes, right? So this one, when I graph it, it's going to kind of look like this, like it's going to shoot up there, and it's just going to kind of level off. That point that it levels off is in the numerator of that equation. So that's going to level off at about 1880. So that population model there, that equation tells me that 1880 is the max amount of fish that I can have in the lake, because that's my asymptote. So that's what this question refers to here. Find the horizontal asymptote. We did. It's on the top there. It's on the top of the equation. What's it represent? Okay, so my horizontal asymptote is 1880, and it represents the carrying capacity of that pond. Represents my carrying capacity of that lake or pond, whatever it is. Okay? And we'll come back to that problem at the bottom there. I want to take care of the next one. So that's the gnats there, because it gives you a nice little graph to use. And the equation is still kind of ugly, but we're going to see if we can figure it out. So graph the function for t is greater than or equal to 0. So this is a population of gnats here. And I'm going to cheat and plug it into my calculator to give you an XY chart fairly quick. So when you're plugging it into your calculator, for you people with a graphing calculator, make sure you put the bottom in parentheses like they have here. You can put it in your calculator, you have to have the parentheses though, otherwise it's not going to graph nice. And then it doesn't matter, like there's a t in the equation, just use x in your graphing calculator. Okay, so for your XY chart, remember I said we could probably go by tens. Let's do 0, 10, 20, 30, and then let's just jump to like 100, and then maybe 200 and see what we hit, just for ease of time here, okay? Because our XY chart, or our graph over there, is going to allow it. So let me give you some numbers. So I'm going to show you what it looks like if I plug a 0 in here. So I have 17,000 over 1 plus 15e. What happens if you put a 0 in here? That just turns into a 0 exponent, right? E to the 0 is just a 1. So you're going to have just 16 on the bottom. 17,000 over 16. That's going to give you 1,062.5. Okay, so that means that's what our population is starting off at, according to this model. And then when we plug a 10 in, you got 1147.2. So that really didn't grow that much, so I'm going to change my XY chart here. You can just change it with me if you want to. I'm going to jump to 100 here. Okay, I'm going to jump to 100 here. And then I'm going to go 200, 300. We'll see what we get closer to there. So if I do x equals 100, let's see if I can get to it on my calculator here. So 100 is going to be, let's start at 50. Okay, at 100, we got 2234.9. And if you wanted to, you can do the math to kind of double check these. I'm just looking at my graphing calculator here to save a little bit of time. So 200 will be 4348.2. And then 300 is 7,451.2. So we got a little bit more change going on, but and that's enough points for us to graph. But remember in the last example I said, what does this number on the top here represent? Let's get some of these arrows out of the way. A number on the top is going to be my carrying capacity or my horizontal asymptote. So we're at 16,000 right here. So that means it's going to level off somewhere up here when I draw my graph. So I don't have to do any more in my XY chart. That's enough. So let's just kind of graph it. So I have 0, 1,062.5. So that would be kind of in here, right in the middle. And then I have 10, 1147.2. So that's really not a whole lot more. And then we jump to 100, and then we're 2234. So 100 is here. 2234 is here. And then we got 200, and that's 4348.2. So 200 is here. 43 is there-ish. And then we got 374.51.2. So 374.51, let's say we're in here-ish. Okay, so this is going to kind of look like this. It's going to be curving up until we get around 17,000. Once we hit 17,000, then it's just going to kind of level off like that. So it's exponential growth to a point, okay? Once it gets to that point, then it levels off. So your horizontal asymptote, that's the next question, x equals 17,000. And that represents our carrying capacity. That's the maximum population. So what's the max population down there? That's that 17,000. And that would be gnats. When does the population reach 15,000? So here's going to be some number crunching for you. So our end result is 15,000, and then we have our equation is 17,000 over 1 plus 15 e to the, what do we got here? 15e to the negative 0.0082 x. So this is the first step is the one that kind of jump starts the rest of it, maybe the first two steps. We need to get this stuff out of the bottom to solve this equation. But we're looking for a time, all right? And that should be a t rather than x. It doesn't matter that much, but I'll just change it back. So we're looking to get that stuff out of the bottom. In order for you to do that, you have to multiply both sides by it. Okay, so I multiply it there, and then I'm going to multiply it over here. Okay, so from there, that's gone, so that canceled out here. Okay, so to save a little bit of space, I'm just going to erase it over here. So we got that out of the bottom by multiplying by it. And now we have this equation written. So now, that stuff there. The bad option here would be to distribute the 15,000. The better option would be to divide the 15,000. Because we can move it from one side to the other with division. So 15,000 there. And I'm just going to put that in my calculator to get a decimal. So 17,000 divided by 15,000. We get 1.133. So 1.133. That's what the fraction on the right-hand side turns to. And on the left, we have this. 82t. Okay? Now we're back to like the problem at the beginning of the lesson. You have to get the e by itself, natural log both sides, and that'll give you your t. So if we move the 1 over, so minus 1, 15 e to the negative 0.0082t equals 0.133. Divide by the 15. And then you're going to have to natural log both sides. So we divide by that 15. I'm going to get rid of this stuff here because I divided it out. I want to natural log both sides. I need to natural log all of that. That'll cancel here. And then you're going to have to divide by that negative 0.0082. So this will be negative 0.0082t equals natural log 0.133 over 15. And I know that these are kind of big problems, so just kind of bear with me. Divide by 0.0082t negative. So that'll cancel there. And you plug that in your calculator and you got it. So natural log of 0.133 divided by 15, close it off. Divide that whole thing by negative 0.0082. Sorry, I don't want the t in the bottom. Get 576 is what we should have. 576.2, we'll round it there, 28 years. Or let me check if this is years or days. Let me see what our problem tells us. It doesn't tell us if it's years or days, so we'll just kind of assume that it's years. So that means my population will reach its max, or it'll reach that, not its max, that 1875, or 15,000, sorry, 1875 was the last problem. Reach 15,000 in 576.28 years. Whew. All right, so we got 3 of those problems knocked down. This one back here, I can show you how to do that on Monday. I'm not going to have enough time in the video to do it, but I'm going to jump to your homework. Okay, so I want you to, you can try to use Desmos for the graphs, and you can sketch them for the things that are involving graphing. So write these problems down, and then I'm going to go to the next slide, which I'll lead you through number 5. So you'll just have to do 7, 8, 9, 10. You'll just have to do 4 of them. Okay? So looking at number 5, that is this. So I would write this down on notebook paper. That way you can just copy this down and have it done as one of your problems. Okay, so we're given a bacteria. It's growing exponentially according to that model. T is the time in minutes. If there are 80 cells initially, 675 cells after 30 minutes, find the value of K for the bacteria. So that's just like the first problem that we did. All right. We have our exponential formula there. Let's plug stuff in. Y, that's what you have in the end. Okay, so we have 675 cells after 30 minutes. So that goes as the Y. All right, 80 is initial, so that's already in our formula. 80e to the kt, so it's 30 minutes, so it's k times 30. So we want to write that as 30k in the top so we don't confuse ourselves. So, divide the 80, natural log both sides, divide the 30, you got what you're looking for. All right, divide the 80. So then I have e to the 30k equals 675 over 80. Natural log both sides. E's cancel out, or the e cancels out there. And then we're going to divide both sides by that 30. So this is what you're putting in your calculator. That's going to give us our value for k. Natural log 675 divided by 80. Close off your parentheses, divide that whole thing by 30, and we get 0.0711. That's the value that we need. Okay, that's our continuous rate of growth value. So for the second one, when the bacteria are going to reach a population of 6,000 cells, we're looking to use the K value to find a time. So we need to find how long it takes us to get to that 6,000. Okay, so 6,000 is going to be the end result. And then we have 80 at the beginning, e to my k, which is 0.0711, and then times the t in the back there. Same exact process. Divide the 80, natural log both sides, divide the 0.0711, and that gives you your t value. So 80. All right, so I can do 6,000 over 80 in my calculator. That'll be an okay decimal. And you can do that if you wanted to as well. You can do this stuff first before you write the natural log. It doesn't matter. So 6,000 divided by 80 is actually 75. So we're going to have 75 equals e to the 0.0711 times t, which from there, natural log both sides. That'll cancel out your e. Divide by 0.0711 on both sides. So when I do natural log of 75 divided by 0.0711, I get 60.72. Okay? These are going to be problems that are similar to the ones on your test. And this is in minutes. Right? So we're doing this in minutes. So we have to pay attention to our labels. You have to make sure that you put your labels at the end. The K value doesn't really have a label because it's a rate, but we have to make sure that we write the correct labels on other things that need it. Okay, so 60.72 minutes. Okay, so for C, I'm not going to go through the whole thing. I'm going to tell you how you would do it, but I'll finish it after the end, just for the sake of people seeing how it's done. You can do that. So you could actually stop the video here and have people work on the homework if you wanted, if you could, please. But I'm going to finish C for people that want to watch the video for a little bit longer. So if you want to, you can go to Google Classroom, find the video, or you can go to my YouTube channel and get it there as well. But if we want to figure out when, so here we're trying to figure out when a bacteria will surpass the other number of cells in that other bacteria. So if it's bigger than, we need to set it greater than or equal to. So we're trying to figure out when is this one going to pass up the other one. So we have 35 e to the 0.0978t. We want that to be greater than our other equation from up above, which we have it up here already. Okay? So that's greater than 80 e to the 0.0711t. So I know all the time before I said first thing you want to do is get the e by itself, but here it just kind of turns into back and forth when you're trying to get the e by itself. So we can actually take the natural log of these both sides here. Okay, natural log of this side, natural log of this side, and then that's all of this stuff inside the natural log. All right, so you're going to have to use properties here to split it up. So we have a 35 times an e on the inside here and a 80 times an e here. So we can split it up with addition. So we have natural log of 35 plus natural log of e to the 0.0978t greater than natural log of 80 plus natural log of e to the 0.0711t. So now you kind of see what happens with the e's, right? Natural log is going to get rid of that stuff. So then we just have those decimals sitting there. So let's put the t, or the decimals with the t in it, to the left, and let's move the other natural log to the right. So this is my step that we're going to do here. We're going to move this one to the left, right? So that is actually moved down from the exponent because I took natural log there, and we're going to subtract that from this one. Okay? And then we're going to move this natural log to the right by subtracting it over here. So minus natural log of 35. Okay? So putting some numbers in your calculator, you're going to have some decimals floating around. That's okay. So we have that 0.0978t minus 0.0711. So then on the left-hand side, we're going to have 0.0267t. And then on the right-hand side, we're going to have natural log of 80 minus natural log of 35. And you can use properties of logarithms to put those together if you want to, but we're just going to kind of do it all at once here. So divide by 0.0267, and that's going to give us our value of t that will tell us when one bacteria will surpass the other one. So natural log of 80 minus natural log of 35. Okay, I'm going to push enter. That'll give me a decimal, which is about 0.8267. And I'm going to divide that by 0.0276. And we get t is greater than 29.95 years. So after 29.95 years, that's when the bacteria will surpass the other one. So we're saying that this little one, or the 35 here, we're saying that that's going to surpass the other one in 29.95 years. Okay? So, or minutes, not years. My apologies. So, where that is in minutes, not in years. Okay? So that is what we get for that one. So that's how you do that. So it's not terrible, it's just a little bit more natural logs than you're used to seeing. So if you got any other questions on that homework, there's 4 of them that you got to go through. Let me know let me know if you got any questions. Send me an email, maybe I can work through them in another video or something like that. So good luck.